In this video, I would like to answer a simple question. According to quantum mechanics, how do you describe a freely moving particle? Now it sounds simple, but what we will discover is that by attempting to answer this question, we will actually uncover one of the most profound ideas in physics, Heisenberg's Uncertainty Principle, which tells us that it's impossible to simultaneously know where a particle is located and how fast it's moving, implying that there is a fundamental limit to our knowledge of the physical universe. It's a principle that lies at the heart of quantum mechanics, and it has revolutionised our understanding of the fundamental laws of physics. So buckle up and get ready for the ride. Our story begins in 1923, when after a long period of reflection, a young French physicist named Louis de Broglie dared to ask the question that if light waves can behave like particles called photons, as had been shown by Einstein's explanation of the photoelectric effect, then is it possible that particles such as electrons can behave like waves? De Broglie's answer to this question was an unequivocal yes. In summary, de Broglie proposed that for a matter particle with mass m moving at velocity v, you can associate a plane wave of wavelength lambda equals h over p, which is equal to h over mv, where p equals mv is the momentum of the particle, and h is Planck's constant. Furthermore, if the particle has energy E, then you can assign a frequency f equals E over h. These relations connect the particle concepts of energy and momentum, E and P, with the wave concepts of frequency and wavelength, f and lambda. De Broglie took the bold step of assuming that these two relationships hold for all matter particles, including electrons, and it was this suggestion that ultimately spurred on Schrödinger to develop his wave equation, which I've covered in a different video titled "What is the Schrödinger equation?" But in this video, I want to take a different direction. So let me now refine the question I posed a moment ago. How do you describe the motion of a freely moving particle if it is to be described by a wave? If you're interested in the answer, stay tuned. Given that the de Broglie-Einstein postulates allow us to assign both a wavelength and frequency to our quantum particle, our first guess might be to describe our quantum particle using a plane wave function of the following form, where the symbol psi is used to represent the wave function, k equals 2 pi over lambda represents the wave number of the wave, which is simply the spatial frequency, and omega equals 2 pi f is the angular frequency of our wave. The velocity of this travelling wave can be calculated by dividing the coefficient of t by the coefficient of x, and if we sub in the explicit expressions for omega and k, we recover the familiar relationship v equals f lambda, which relates the wave speed, wave frequency, and wavelength. Next, if we take the Einstein-de Broglie relations and rewrite them in terms of f and lambda, then we should be able to re-express the wave velocity in terms of the energy and momentum of the associated particle. If we sub in the expressions for f and lambda, we find the following expression, and if we simplify, we find that the wave speed is equal to E over p. Now, if we wish this travelling wave to somehow describe our freely moving particle, then we would expect that the velocity of our wave is equal to the velocity of our particle. So is this the case? For a freely moving particle with mass m travelling at velocity v subscript p, where p stands for particle, we know that the energy of the particle is given by E equals half mvp squared, and the momentum of the particle is given by p equals mvp. And if we sub these expressions into the wave velocity equation and then simplify, we find the rather startling result that the velocity of the wave is equal to half the velocity of the particle. And so we see that we have a bit of a problem. Apparently, the quantum mechanical wave function travels at half the speed of the particle that it's meant to represent. So what has gone wrong? Unfortunately, this is not the only problem associated with describing a particle with a plane travelling wave. According to quantum mechanics, the wave function, psi of xt, provides information about the probability of finding a particle in a particular region of space. In other words, if at some instant in time t, a measurement is made to locate the particle associated with the wave function, then the probability that the particle will be found at a coordinate between x and x plus dx is equal to the modulus squared of the wave function multiplied by dx, where, if you recall, the modulus squared is equal to the complex conjugate of the wave function multiplied by the wave function itself. If we then want to find the probability that the particle is located within a given region, we simply need to integrate the modulus squared. So, for example, the probability of finding a particle located in the region x is greater than or equal to a and less than or equal to b would be given by the integral from a to b of the modulus squared dx. So what does this imply for our proposed plane wave function a cos kx minus omega t? Well, if we take the modulus squared of this function, we find the answer of a squared cos squared kx minus omega t. Now, assuming that our particle must exist somewhere in space, we would expect that the integral of this expression, evaluated from minus infinity to plus infinity, must be equal to 1. However, if we perform the integral, we see that we end up integrating cos squared kx minus omega t from minus infinity to plus infinity. And since cos squared is always positive, the integral does not converge, and we would get an infinite result. In other words, the plane wave function is non-normalizable. And so we see that in the case of a free particle, a plane wave function does not represent a physically realizable state. Something has gone wrong. So to summarize, we've just seen that a plane wave function leads to an incorrect velocity and a non-normalizable wave function. So what is the cause of these problems? Well, the source of the problem is the plane wave function that we've been using to describe our freely moving particle. Not only did this lead to a nonsensical probabilistic interpretation, it also led to the ludicrous result that the wave must be travelling at half the speed of the particle it's meant to represent. Now, since a particle is, by definition, an object that is localised in space, it is perhaps not surprising that our spatially extended plane wave has failed to do the job. Since the wave function tells us information about where we are most likely to find our particle, perhaps the solution to our problem is to construct a wave function that is localised in space. So how exactly do you create a localised wave function? Well, the answer turns out to be incredibly interesting. To create a single isolated wave packet, we need to add together multiple waves with slightly different wavelengths using the principle of superposition. To show how the principle of superposition works, consider adding together two wave functions psi1 and psi2, where psi1 equals cos kx minus omega t and psi2 equals cos k plus delta kx minus omega plus delta omega t. In other words, the wave number of the second wave function is shifted by a small amount delta k relative to the first wave function, and the angular frequency is shifted by a small amount delta omega. Next, we can combine psi1 and psi2 by making use of the following trigonometric identity. Applying this to our two wave functions, we find the following yellow expression. Next, if we assume that delta k and delta omega are very small compared with k and omega, then we can write that 2k plus delta k is roughly equal to 2k, and 2 omega plus delta omega is roughly equal to 2 omega. If we then sub this back into our expression, we see that the second cosine term dramatically simplifies, and as a result, our combined wave function expression takes the following simple form. So what does this combined wave function look like? If we plot the two separate wave functions and then the combined wave function underneath, we find the following result. We see that the effect of combining the two wave functions is to produce a series of wave packets that move at a different velocity to the individual waves comprising them. Let's take a closer look and plot this function at a fixed time t equals 0. We notice from the combined wave function expression that there are two cosine terms multiplying each other. The second cosine term, cos kx minus omega t, is exactly the same plane wave expression that we had earlier. However, the presence of the first cosine term modulates the amplitude, and as a result the oscillations fall within a periodic envelope defined by the first term. This is due to the fact that the two component wave functions have slightly different values of k and omega, and therefore alternately interfere and reinforce in such a way as to produce a succession of groups. These groups and the individual waves they contain are both moving in the same direction of increasing x. Furthermore, we notice that the velocity of the individual waves is different to the velocity of the whole group. So our next task is to investigate this difference. The velocity of the individual waves can be evaluated by considering the second cosine term. As we've already seen, the velocity of these waves can be calculated by dividing the coefficient of the t term by the coefficient of the x term, in which case we have that the velocity of the wave is equal to omega over k. To find the velocity of the group, we look at the first cosine term and again divide the t coefficient by the x coefficient, in which case we get the following result. Now, in the limit that delta omega and delta k go to 0, we can write the group velocity as the derivative of the angular frequency with respect to the wave number. So, can we calculate this? Well, firstly we need to determine omega for a freely moving particle. To do this, we can combine E equals hf with omega equals 2 pi f, and we see that omega equals E over h bar. Next, we know that for a freely moving particle, E equals half mv squared and P equals mv, and therefore we can write the energy as E equals P squared over 2m. If we then substitute this into our expression for omega, we find that omega is equal to P squared over 2m h bar. Next, if we combine the de Broglie relation P equals h over lambda with the wave number definition k equals 2 pi over lambda, we see that the momentum can be written as P equals h bar k. And if we sub this into our omega equation, we find that omega is equal to h bar k squared over 2m. And so now that we have an expression for omega in terms of k, we can substitute this into our group velocity equation, in which case we have the following expression. Next, if we perform the differentiation, then we find that the group velocity can be written as h bar k over m. And because h bar k is equal to p, we see that the group velocity can be written as p over m. And finally, because for a freely moving particle, the momentum p can be written as the mass of the particle multiplied by the velocity, it follows that the group velocity is equal to mvp over m, which simplifies to vp. In other words, we have just shown that the group velocity of the wave packet is equal to the velocity of the particle that it's meant to represent. And so to summarise, we see that when we form a group of waves using the principle of superposition, then although the individual waves do not travel with the velocity of our particle, the group itself does. We do, however, still have a problem. If the wave function describing our particle represents information about where the particle is likely to be located, then our previous analysis is insufficient, as we have multiple wave packets rather than a single isolated wave packet. So how can we create a single wave packet? To answer this question, we will begin with a simple example. Let's consider the superposition of 5 waves, each of the form a cos kx. To simplify our analysis, we will set t equal to 0, which is why there is no time dependence inside the cosine expression. This simply means that we are considering a fixed moment in time. We will consider the more subtle question of time evolution at the end of the video. Next, we will assume that all of our waves have the same amplitude which we will take to be 1.0 in some arbitrary unit system, which is not important for the time being. We will also assume that the k values of each wave differ by pi radians per meter, ranging from k equals 10 pi to k equals 14 pi. To make this explicit, let's write out the individual wave functions for each of the 5 waves. What we now want to do is form the superposition of these 5 waves, which simply means we want to add together the individual wave functions. We can write this in a more compact form as the sum from n equals 1 to 5 of an cos knx, where the ans and kns take the following values. Now, it will prove useful for our analysis later to show how we can represent this superposition of waves graphically by plotting a graph with amplitude on the y-axis and wave number on the x-axis. For our example, we have 5 equal amplitude waves with wave numbers of 10 pi, 11 pi, 12 pi, 13 pi and 14 pi respectively, corresponding to each wave function. And we see that this corresponds to 5 equal height lines on our amplitude versus wave number graph. This is often referred to as the k-space representation of the superposition, since we are plotting the wave number k on the x-axis. So let's now see what happens when we add these 5 waves together. We notice that due to the difference in k values between the 5 waves, when we superimpose the 5 waves on top of each other, there are regions where the waves perfectly overlap, and there are regions where the peaks of some of the waves coincide with the troughs of other waves. According to the principle of superposition, the waves will add together where the waves overlap perfectly, and they will tend to cancel out where peaks and troughs coincide, and the net result will be like the pattern shown. We see that the result of adding 5 waves with k values differing by pi radians per meter has been to create a series of spatially separated wave packets. We also notice that in between the wave packets there are smaller oscillations, and these occur because when we added together the 5 waves, they did not perfectly cancel in these regions. And so we have 2 problems that require a solution. Firstly, how do we get rid of the smaller fluctuations in between the wave packets? And secondly, how do we get rid of the additional wave packets? To answer these questions, we will have to develop our understanding of the superposition of waves. But to begin with, let's see what happens if we simply add more waves together and reduce the difference in wave number between each wave. Previously, we considered the superposition of 5 equal amplitude waves with k values that differed by pi radians per meter. Let's now add an additional 4 waves such that the difference between each is pi over 2 radians per meter. You can see this represented in k-space on our graph by the 9 equal length vertical lines, and as before, we can write this superposition of waves as the sum of an cos knx, where now n runs from 1 to 9. If we line up each of these 9 waves and then superimpose them on top of each other, we again see that there are regions where the waves coincide and regions where they do not. If we then explicitly add these waves together and look at the net amplitude, we find the following pattern. If we then compare this with our previous 5-wave pattern, we see that the net effect of adding more waves within the same k range, but with a smaller difference in k values, is that the wave packets are now more spread out, with a greater space between individual wave packets. So perhaps this is hinting at a strategy for producing a single isolated wave packet. We simply need to add more waves and reduce the difference in wave number between the waves. And so a natural question arises. What happens if we add together a continuous spectrum of k values within the same range as before? Can we explicitly calculate what the net result of this superposition would be? Well, thankfully, the answer is yes. So let's do that. Let's consider a situation in which we have a small range of k values, labelled delta k, centred around a k value that we will label k0. It then follows that the lowest k value will be equal to k0 minus delta k over 2, and the highest k value will be equal to k0 plus delta k over 2. We will again assume that all of our waves have the same amplitude, and so we can specify the continuum of k values by stating the following condition, that a of k is equal to 1 in the given range, and a of k is equal to 0 for all other k. Our task is to now find an expression for the superposition of this continuum of waves. So how do we do that? If you recall, when we were dealing with discrete values of k, we were able to calculate the superposition of our wave functions by simply adding together the separate functions. However, when dealing with a continuum of k values, we need to replace our discrete sum with a continuous integral of the following form. We recognise that this has the same general structure as before, only now our amplitude is a function of the wave number, and we write this as a of k. Furthermore, instead of summing over n discrete k values, we integrate over all k values from minus infinity to plus infinity. And finally, we include a standard 1 over the square root of 2 pi normalization factor. This expression actually has a name. It is referred to as a Fourier transform, and this general type of integral plays a key role in the mathematics of waves and vibrations. Our task is to now use this integral expression to calculate the resultant wave function corresponding to the amplitude function we have just specified. If we sub in a of k equals 1 and change the limits of our integral, we arrive at the following expression. So our next task is to calculate this integral. Well, thankfully this is a relatively straightforward task. We are integrating cos of kx with respect to k, and so when we perform the integral, we get sine of kx over x. If we then sub in the limits of our integral, we find the following yellow expression. We can simplify this by making use of the following well-known trigonometric identity. Applying this to our wave function, we find the following result. The final step is to multiply the top and bottom of this expression by delta k over 2, in which case we find that the wave function can be written in the following equivalent form. So let's take a closer look at this function. We see that it comprises a cosine term multiplying a term in brackets involving sine of delta k x over 2 divided by delta k x over 2. If we were to plot the first cosine term on its own, we would find something that looks like this. Whereas if we were to plot the term inside the brackets, we would find something that looks like this. So what would the product of these two terms look like? To answer this question, let's plot a graph of our wave function with the x-axis representing the x position and the y-axis representing the value of our wave function. If we then plot the wave function, we find the following pattern. We see that we have a large central wave packet lobe with a series of much smaller side lobes to the left and right. At first glance, this does not look any better than our earlier attempts to create an isolated wave packet. However, if we zoom out a bit, and then a little bit more, we see that the large central lobe and side lobes are indeed localized in space, and as we move off in the positive or negative x direction, the amplitude of the wave function reduces to 0. And since the wave function tells us information about where we are most likely to find our particle, we have at least partially succeeded in confining the particle to a smaller region of space than when we had a periodic series of wave packets spreading throughout all of space. So let's pause a moment and take a closer look at this localized wave function. If we plot the function, then we notice that the rapidly oscillating green wave corresponds to the cosine term in our wave function, whereas the dashed purple line corresponds to the sine term inside the brackets. Next, notice that there are a series of points along the x-axis between the lobes where the wave function reduces to 0. These zeros correspond to the locations where the sine term inside the bracket reduces to 0. If we label the zeros either side of the central lobe as minus x0 and plus x0, then we can use these points to specify the width of our central wave packet. So can we actually determine this width by calculating the value of x0? Well, as already mentioned, when x equals x0, our wave function psi of x equals 0. And this occurs when sine of delta k x0 over 2 equals 0. And as you probably know, this first occurs when the argument of the sine function is equal to pi radians. In other words, when delta k x0 over 2 equals pi. And this implies that x0 equals 2 pi over delta k. Okay, but what is this x0 relationship telling us? Well, if you recall, x0 tells us the width of the central wave packet. And if we look at the x0 relationship, we see that as delta k decreases, x0 increases, which is to say that the width of our wave packet increases. And since the wave packet tells us information about where we are most likely to find our particle, if the width of the wave packet increases, our uncertainty in where the particle is located must also increase, and we label this uncertainty delta x. Likewise, as delta k increases, we see that x0 decreases, and therefore our uncertainty in where our particle is located also decreases. We can summarize this result by saying that the product of delta k and delta x is equal to a constant, so that as one increases, the other decreases, and vice versa, as can be seen in the animation below. This is telling us that if we use a smaller range of k values, then when we superpose these waves, the resultant wave packet will be broader than if we had used a wider range of k values. We also notice that when delta k is equal to 0, this corresponds to a single plane wave with constant wavelength, in which case there is no superposition, and our wave will extend throughout space, meaning that the uncertainty in the particle position would be infinite. Now at this stage, it's worth noting that we can recast the condition that delta x times delta k equals a constant into a more suggestive form. If you recall, the momentum of a particle can be related to its wave number via the relation p equals h bar k, and therefore it follows that a large range of k values amongst our component waves corresponds to a large range of possible momentum values of our particle. And so we see that we could equivalently write our delta x delta k condition as delta x times delta p equals a constant. In other words, the uncertainty in the position of the particle multiplied by the uncertainty in its momentum is equal to a constant. This is telling us, for example, that if we have a narrow wave packet which corresponds to a small uncertainty in where our particle is located, then this will correspond to a large uncertainty in the momentum of our particle, and vice versa. Now the sharp-eyed amongst you will recognise this condition as being reminiscent of Heisenberg's uncertainty principle, and you wouldn't be wrong. We will certainly have more to say about this later, but before we get ahead of ourselves, we still have a few issues that require fixing. We have just seen that by using a continuous range of component wave functions, each with the same amplitude, we have managed to create a partially localized wave packet consisting of a large central lobe and multiple smaller side lobes. So the next question is, how do we get rid of the side lobes? Well, one thing that we haven't yet considered is what happens if our component waves do not all have the same amplitude. In other words, what happens if we modulate the amplitude of our waves? So let's find out. To start with, let's return to our 5-wave example with k values differing by pi radians per meter and plot a graph in k space, only this time we will modulate the amplitude of our waves so they fit inside a Gaussian curve. I'll have more to say about Gaussian bell-shaped curves a bit later, but for now, simply notice that, for example, psi1 and psi5 have very small amplitudes, and so they will not contribute as much to the net wave function, whereas psi3 has a larger amplitude and therefore will contribute a greater amount when we add all the waves together. We can visualize each of the component wave functions in position space by plotting the corresponding cosine waves, and this makes the differences in amplitudes manifest. If we then superimpose the waves on top of each other, we see that there are regions where the waves perfectly overlap and regions where they do not. What we now want to do is calculate the superposition of these 5 waves. If we use the principle of superposition to add together the waves, we find the following resultant wave function pattern. Now, it's worth comparing this with the constant amplitude 5-wave example we looked at earlier. We see that the effect of modulating the amplitude of our waves is to remove the small fluctuations that existed between each wave packet. And so we see that the resulting wave packets are more clearly defined in space. However, we encounter the same issue that we previously encountered when considering 5 waves with equal amplitude, namely the fact that there are still multiple wave packets. And so we will follow the same logic as before and improve our situation by adding together more waves and reducing the difference in wave number between the component waves. So let's do that. And so, if we take our modulated amplitude example, but this time consider the superposition of 9 waves, each differing in k value by pi/2 radians per meter, then we can represent this in k-space using the following Gaussian distribution of amplitude values. If we were to visualize each of the component waves, we would see the following distribution, and if we superimpose these on top of each other, we again notice regions in which all the component waves perfectly overlap, and regions where they do not. If we then apply the principle of superposition to add these component waves together, we find the following resultant wave function pattern. And if we compare this to the 5-wave modulated amplitude example we saw earlier, then we see that by increasing the number of component waves to 9, and by reducing the difference in wave number between the waves, we have managed to increase the space between adjacent wave packets, whilst at the same time minimizing the small fluctuations between the wave packets. And so hopefully now it should be obvious what the next logical step is. To obtain a single well-defined isolated wave packet, we need to add together an infinite number of waves that differ infinitesimally from each other in their k value. From a k-space perspective, this would correspond to adding a continuum of k values with amplitudes that fit inside a Gaussian envelope. The Gaussian envelope represents the amplitude function a of k, which tells us how the amplitude of our component waves are modulated for different k values. And so to summarise, our claim is that the superposition of a continuous distribution of k values, with amplitudes modulated so that they fit inside a Gaussian curve, will lead to the creation of a single well-defined isolated wave packet, and that this wave packet will provide probabilistic information about where we are most likely to find our particle. And so our next question is, how do we describe this wave packet mathematically? Well, the good news is that we've already laid some of the foundations. We have already seen that for a continuous distribution of k values, the resultant wave function can be calculated using the following integral expression. Now, there is one small change that we will make to this equation, and this is a reflection of the fact that in quantum mechanics, the wave function is generally a complex function involving imaginary numbers. As a result of this, we will replace the cos kx term appearing inside the integral with an e to the I kx term, where, if you recall from my video on the Schrödinger equation, Euler's identity tells us that e to the I kx is equal to cos kx plus I sine kx. And so we see that if we take the real component of our composite wave function, then we recover the same expression that we had before. Our ultimate goal is to use this general integral expression to calculate the wave function corresponding to our localized wave packet. To do this, we first need to specify the form of the amplitude function a of k, and as I've already mentioned, we will be assuming that a of k is described by a Gaussian distribution. And so our next immediate task is to understand how to mathematically describe a Gaussian distribution. So let's do that. A Gaussian distribution, also known as a normal distribution, is a characteristic bell-shaped continuous probability distribution and can be represented by the following rather ghastly mathematical function. where the mean value of x corresponds to the peak of the curve, and sigma x represents the standard deviation of the Gaussian distribution, which, if you recall, is defined as the square root of the difference between the mean of the square of x and the square of the mean of x. You can think of the standard deviation as a measure of the spread or width of the distribution, and within the context of quantum mechanics, the standard deviation in x is often referred to as the uncertainty in x. The function p of x is referred to as the probability density function, and if, for example, we wanted to find the probability that our x value lies between a value of x and a value of x plus dx, then this would be equal to p of x times dx. What is important for us is the p of x function itself. To emphasize the relationship between the standard deviation, sigma x, and the width of our Gaussian distribution, let's plot our Gaussian function and then slowly increase the value of sigma x appearing in our probability density function. We see that as sigma x increases, the width of our distribution increases, and so we can conclude that sigma x is a good measure of the width of our Gaussian distribution, since it controls how quickly the exponential term appearing in the probability density function approaches zero. The final thing worth mentioning is that the constant coefficient term multiplying the exponential is a normalization factor that ensures that when we add up all of the probabilities corresponding to each of the different values of x, the sum total will be equal to 1, as is required for a probabilistic interpretation. This is equivalent to requiring that the integral of the Gaussian distribution, evaluated from minus infinity to plus infinity, is equal to 1. So, can we show that this is true? Well, thankfully the answer is yes, but in order to do so, we will need to take a very quick detour and remind ourselves how to evaluate Gaussian integrals. So let's quickly do that. Let's consider a simplified form of a Gaussian integral in which we define I as the integral of e to the minus x squared dx, evaluated from minus infinity to plus infinity. To begin with, because of the symmetrical shape of the function, we can write this as 2 times the integral of the same function from 0 to infinity. Next, consider the square of this expression, I squared. In other words, consider multiplying the integral of e to the minus x squared dx by the integral of e to the minus y squared dy. We can then combine the exponential terms and write I squared as a double integral. So how do we evaluate this integral? At first appearance, this doesn't look any better than the integral we started with. But there is a trick, and the trick is to change variables. If we define y equals xt, then we see that t equals y over x and dy equals x dt. And the limits of our y integral change from y equals 0 and y equals infinity to t equals 0 and t equals infinity. If we then substitute this change of variables into our expression for I squared, we find the following pink expression. And if we then pull out a factor of x squared out of the bracket appearing in the exponential, we find the following green expression. Next, we change coordinates again and let u equal minus x squared times 1 plus t squared, in which case du equals minus 2x times 1 plus t squared dx. And as a result of this change of variables, the integral limits will range from u equals 0 to u equals minus infinity. If we sub these relations into our expression for I squared, we find the following yellow expression. We can now perform each of the integrals separately. Firstly, the integral of e to the u du from 0 to minus infinity is equal to minus 1. And that just leaves the integral of 2 times 1 over 1 plus t squared, evaluated from 0 to infinity. This is a standard trigonometric integral, which is equal to 2 tan to the minus 1 of t, evaluated between the limits of t equals 0 and infinity, and this is simply equal to pi. And so when the dust is settled, we see that I squared equals pi, and therefore it follows that our Gaussian integral, I, is equal to the square root of pi, and we arrive at one of the most famous results in mathematics. which is the fact that the integral of e to the minus x squared, evaluated from minus infinity to plus infinity, is equal to the square root of pi. This is known as a Gaussian integral. Now, it's a relatively straightforward exercise to generalize this analysis and consider the more general Gaussian integral, where b and c are constants, and we find in this case that the integral is equal to the square root of pi over b. And this is the result we were looking for. We can now go back to the original Gaussian expression that we started with and use the result we've just derived to show that the Gaussian function is normalized. We simply set b equal to 1 over 2 times sigma squared, in which case our integral takes the following form, and this just simplifies to 1 as required. Okay, so let's just pause a moment and take stock of where we are and what we've achieved so far. We have just had a crash course in Gaussian distributions and have found that the function p of x describes a normalized Gaussian distribution, and that the width of the function is characterized by the standard deviation sigma. If you recall, the reason we were looking at Gaussian functions in the first place was because when we were trying to construct a localized wave packet, it was necessary to add together an infinite collection of waves whose amplitudes differed in some way, and we found that if the amplitudes of the component waves were modulated according to a Gaussian distribution, then when the waves were superposed, the resulting wave packet was localized in space. So what we now want to do is to show this explicitly by calculating the shape of the wave packet in the case where our amplitude function a of k takes the form of a Gaussian distribution. To do this, we will specify our a of k so that it takes a Gaussian form, where alpha is a constant. The specific choice of coefficient will become clear shortly once we've constructed our wave function, so let's do that. We now have all the necessary ingredients to calculate our wave packet wave function. We simply need to substitute the explicit form of a of k into psi of x and calculate the resulting integral. If we perform the substitution, we find the following result, and this is what we now need to calculate. So, how do we solve this integral? Well, the first thing that we can do is rewrite the integral in an equivalent form such that each exponential term includes a factor of k minus k naught. Next, we let k prime equal k minus k naught, in which case we see that dk prime by dk equals 1, and therefore dk prime is equal to dk. As a result of this change of variables, our wave function takes the following form. So what next? Well, the trick is to combine the exponents in the two exponential terms and then strategically rewrite these terms in the following form. If we then insert this back into our integral, we can separate out the exponentials again, and we find the following green expression. Next, we can change variables again and define k double prime equals k prime minus ix over 2 alpha, from which it follows that dk double prime is equal to dk prime. If we then substitute this change of variables into our wave function, we find the following yellow expression. Next, we notice that as a result of this change of variables, we are left with a standard Gaussian integral, and so we can use our result from earlier, which tells us that the integral will be equal to the square root of pi over alpha. And so, when the dust has settled, we see that our wave function takes the following form. And if we simplify this expression, we finally arrive at the result that we were looking for. We have successfully managed to calculate an explicit expression for the wave function for the example of a Gaussian amplitude function. So how do we interpret this result? What does this wave function look like? Well, firstly, we notice that the wave function contains a complex exponential term, as well as a Gaussian exponential term. We can visualize this function by looking at its real component, in which case we find the following result, where we've made use of Euler's identity, which, if you recall, says that e to the I kx is equal to cos kx minus I sine kx, and the real part is the part that involves no factors of I. So let's now plot this function and see what we get. If we plot the real part of the wave function on the y-axis and the x position on the x-axis, then we get the following wave function distribution. And we can finally rejoice as we have managed to construct a well-defined, isolated wave packet, which is precisely what we set out to achieve. Now, I'm not sure about you, but I find it incredibly satisfying to see the mathematical form of this wave function emerge from our detailed analysis. Our next step is to provide a physical interpretation of this result. So let's do that. As mentioned earlier, according to the quantum mechanical framework, the position space wave function provides information about where we're most likely to find our particle. And as we've already seen, the probability of finding a particle between a location x and x plus dx is given by the modulus squared of the wave function, and this is crucially important because it's actually the modulus squared of the wave function, rather than the wave function itself, that provides information about the probability of finding a particle in a particular region of space. And so our next task is to take the localized wave packet wave function that we've just derived and calculate the modulus squared. To do this, we first need to calculate the complex conjugate of our wave function, and to do this, we simply replace the i's with minus i's, in which case we find the following expression. If we then calculate the modulus squared, we see that the complex exponentials have disappeared, and we are left with a purely Gaussian probability density function, which we can visualize by plotting the modulus squared on the y-axis and the position on the x-axis. And we see that the modulus squared function does indeed have the same shape as a Gaussian distribution, with the mean value centered at the origin. And it is the width of this distribution that we're interested in, as this will provide us with information about where the particle is likely to be located, and therefore the uncertainty in the location of our particle. So let's just pause a moment and take stock of where we are. We have just seen that the modulus squared of our wave packet wave function represents a probability density distribution that is Gaussian in shape. Furthermore, we saw earlier that a general Gaussian probability density distribution takes the following form. If we then assume that our general Gaussian distribution is centered at the origin, we see that our modulus squared wave function has exactly the same structure as the Gaussian probability density function p of x. And so let's see what happens if we compare terms in these two expressions. A quick glance tells you that the two expressions are identical provided that alpha equals sigma x squared, which implies that sigma x equals the square root of alpha. And so we see that the modulus squared of our wave function represents a Gaussian probability density distribution of our particle's position with a standard deviation given by the square root of alpha. We will come back to this shortly. Now, in much the same way that the modulus squared of our position space wave function provided information about the probability distribution of the particle's position, it turns out that if we take the amplitude function a of k and calculate the modulus squared of this, then this represents the probability density distribution of the particle's wave number. We can see this explicitly by plotting the modulus squared of a on the y-axis and the k value on the x-axis, and we see that we do indeed get a Gaussian distribution centered at k0. It therefore makes sense to compare the modulus squared of our amplitude function with the general Gaussian probability density function, only this time note that p is a function of k rather than x. If we compare terms, then we see that the expressions are identical provided that 2 alpha equals 1 over 2 times sigma k squared. If we rearrange this, we see that sigma of k is equal to 1 over 2 times the square root of alpha. And so we conclude that the modulus squared of our amplitude function represents a Gaussian probability density distribution of our particle wave number with a standard deviation given by 1 over 2 times the square root of alpha. So let's pause a moment to gather our thoughts. We took the wave packet wave function and the amplitude functions that we determined earlier, and then we looked at the modulus squared of each, as these tell us something about the probability of finding a particle within a certain region of space or within a certain wave number range, respectively. We found expressions for the standard deviations of these probability distributions by comparing the modulus squared expressions with the general expression for a Gaussian probability distribution, and we found the following two results. Now, since the standard deviation provides information about the spread or width of the corresponding probability distribution, it is often referred to as the uncertainty, and so we will follow convention and refer to the uncertainty in x and the uncertainty in k. And so we should really write delta x equals the square root of alpha and delta k equals 1 over 2 times the square root of alpha. Next, observe what happens if we multiply these two uncertainties together. We see that the product of the uncertainties is equal to half, and therefore we see that delta x times delta k equals 1/2. So what does this mean? Well, one way of visualizing this result is to plot both the amplitude function a of k and the real part of the corresponding wave packet wave function, and then observe what happens to the width of the wave packet as the width of the amplitude function decreases. We see that as a of k gets narrower, which corresponds to delta k getting smaller, the width of the wave packet increases, which corresponds to delta x increasing. And furthermore, we see that the change in delta x and delta k are such that the product of these two always remains equal to 1/2. Now, we saw earlier that the wave number is related to the momentum by the relationship p equals h bar k, and so it follows that delta p equals h bar delta k, and therefore we can write delta k is equal to delta p divided by h bar. And if we sub this into our delta x delta k expression, we find that delta x times delta p over h bar is equal to 1/2. And if we rearrange this, we find a rather remarkable and perhaps familiar result. We see that the uncertainty in particle position multiplied by the uncertainty in particle momentum is equal to the reduced Planck's constant divided by 2. This expression is telling us that there is a fundamental limit to the precision with which the position and momentum of a particle can be known. We see that as we reduce the uncertainty in the particle's position, this leads to an increase in the uncertainty in the particle's momentum. And likewise, if we reduce the uncertainty in the particle's momentum, then we necessarily increase the uncertainty in the particle's position. And the beautiful thing is that we can now understand where this relationship comes from in terms of wave packets and the principle of superposition. Now, it is worth emphasizing that we have arrived at this result by considering a Gaussian-shaped amplitude function. It turns out that if you repeat the analysis for any other amplitude function, then you will find that the product of the position and momentum uncertainties will be greater than h bar over 2. And therefore, the most general statement that we can write down is that delta x times delta p is greater than or equal to h bar over 2. And this statement is known as Heisenberg's Uncertainty Principle. It is saying that precise knowledge of position is incompatible with precise knowledge of momentum, since the product of their probability distribution uncertainties, delta x times delta p, must be greater than or equal to h bar over 2. Now, you might think that this would be a natural point to end the video, but we haven't actually answered the question posed at the beginning, which was to find out how to describe the motion of a freely moving particle. So far, we've not included time in our analysis. And so to end this video, I would like to briefly discuss what happens to our wave packet when we introduce the dimension of time. To begin with, consider a particle moving in the positive x direction, which, at time t equals 0, is described by a wave packet that has an initial uncertainty in position of delta x naught and an initial uncertainty in momentum of delta p naught. And we can relate this to the uncertainty in position using Heisenberg's Uncertainty Principle. Then the uncertainty in the particle's momentum leads to an uncertainty in the particle's velocity given by delta p naught over m. And if we sub in the expression for delta p naught that we just calculated, we find that the uncertainty in the particle velocity is given by h bar divided by 2m delta x naught. Now, this uncertainty in the wave packet velocity means that different parts of the wave packet will move with different velocities, causing the width of the wave packet to increase with time. After t seconds, we would expect the width of our wave packet, delta x of t, to be roughly equal to the uncertainty in the velocity multiplied by the time t, which gives a result of h bar t divided by 2m delta x naught, where, as you recall, delta x naught is the initial width of the wave packet. This expression is showing us that as time increases, the width of our wave packet will also increase. And we also see that if we try to make the initial wave packet very small, so that delta x naught approaches 0, then delta x of t will approach infinity. And so we see that the more a wave packet is confined, the faster it will expand. And so our final task before we end this video is to ask the question, can we determine the time-dependent wave function so that we can understand the evolution of our wave packet as time progresses? To begin with, recall our earlier analysis where we were able to calculate the time-independent wave packet wave function, psi of x, by substituting in the Gaussian amplitude function and then solving the integral. Now, we can introduce time dependence by simply multiplying our time-independent wave function by the factor e to the minus I omega t, in which case we find the following expression for psi of xt. We see that the e to the I kx term has become an e to the I kx minus omega t term. And we have written omega brackets k to highlight the fact that omega is a function of k. For our free particle, this simply means that the energy depends on the momentum. Next, if we sub in our Gaussian amplitude function a of k, we find the following green expression. Now, if you recall from our early analysis, the trick to solving this integral was to simplify the integrand by changing variables to k prime equals k minus k naught. However, we now have an e to the minus I omega t term appearing in our integral, which we didn't have before. So what do? Well, the solution is to perform a Taylor series expansion of omega of k around the centre of the wave packet k naught in k space. In other words, we are going to write omega of k equals omega of k naught plus d omega by dk evaluated at k naught times k minus k naught plus half times the second order derivative of omega with respect to k evaluated at k naught times k minus k naught squared plus higher order terms. Now, the reason for doing this is it allows us to express omega of k as a series of terms, each of which involves a factor of k minus k naught. We will ignore the higher order terms at this stage as their contribution will be negligible for the calculation that follows. Now we can neaten this up a little bit by noticing that the derivative of omega with respect to k is simply the group velocity of our wave packet which we encountered earlier. And to streamline our notation further, we will also define beta as being equal to half times the second order derivative of omega with respect to k, and omega naught as being equal to omega of k naught. This then allows us to write the omega k expansion in the following form. If we then sub this expansion back into our wave function expression, we find the following yellow equation. And if we then make the substitution k prime equals k minus k naught, we can rewrite the wave function in the following form, where we have pulled out a factor of e to the I k naught x minus omega naught t in front of the integral. Next, if we compare this rather horrendous expression with the time-independent expression for psi of x we encountered earlier, which, if you recall, had the following Gaussian solution, then we see that our time-dependent wave function, psi of xt, has exactly the same form as the time-independent wave function, psi of x, provided we make the following substitutions. And so, rather than having to go through the pain of solving our horrific time-dependent integral, we can simply write down the answer by taking the time-independent solution and then making the substitutions contained within the red box. If we do this, we find the following beautiful expression for our time-dependent wave packet wave function. So what is this wave function telling us, and can we visualize it? Well, let's begin by plotting the real part of this wave function and observe how it evolves with time. If we do that, we see that the wave packet spreads and widens as the wave packet moves through space. So does this mean that the particle itself is, in some sense, spreading out? Well, the answer is no. If you recall, the wave function provides information about the probability of finding the particle at a particular location in space. To be more precise, it's the modulus squared of the wave function that tells us the probability density. And so let's quickly calculate this and see what we get. Recall that the probability density is given by the modulus squared of the wave function, and if we calculate this for our time-dependent wave function, we find the following expression. And if we plot this, we see that the width of our probability distribution increases with time, meaning that the uncertainty in the particle's location also increases with time, which is precisely what we argued earlier. And so there you have it. If you've managed to follow up to this point, then well done. I hope that you now have a slightly better understanding of how a freely moving particle is described within the framework of quantum mechanics. And furthermore, I hope that you see the deep link between our probabilistic wave packet description of a particle and Heisenberg's uncertainty principle. I think it only appropriate that we end with the words of Werner Heisenberg, who said, "The existing scientific concepts cover always only a very limited part of reality, and the other part, that has not yet been understood, is infinite. Whenever we proceed from the known into the unknown, we may hope to understand, but we may have to learn at the same time a new meaning of the word understanding." I hope you've enjoyed this video, and I'll see you next time.